got an exponent starting at e power minus at, starting at negative infinity, is neither an energy nor a power signal for any real value of a. However, if a is purely imaginary, it is a power signal with power pg is equal to 1 regardless of the actual imaginary value of a. Okay, we have to prove this one. Now let's look at the case 1. So in the case 1, what we have to do is we have to prove that this e power minus at is not a not an energy signal or power signal when the a values are real values. Okay, a is a real value. That's the thing where no a is real value for the first case. And in this case, we are going to analyze the energy signal and the power signal of this given function. And the energy signal can be calculated by this using this formula. Eg is equal to integration negative infinity to infinity g of t absolute value square dt. This is the equation for the energy signal. Now from the given function we can apply this e power minus at for this g of t. So this is negative infinity to infinity e power minus at square dt. Okay, so if we square negative 80, that's gonna become minus 2, because if you square an exponential, that multiplies. So we will end up with integration negative infinity to infinity e power minus 280 dt. Okay, now let's do the integration. So if you do the integration, this is gonna become e power minus 280 divided by the coefficient in front of it, that is in front of this t, that is minus 2a in this case, and the limit goes from negative infinity to infinity. And this is 1 over minus 2a is a constant, because this infinity, negative infinity, since we are integrating this with respect to t, we have to just apply this in negative infinity and infinity for the t value. This is 1 over minus 2a in front, and then here we are going to have upper limit first, that is e power minus 2a t, that is okay. Let's put this one this right for now. And then we are going to have minus the e power, oh, okay papa, okay papa. So okay, 1 over minus 2a. Okay, so this one, instead of putting like this, let's move. Since we are just gonna apply just this value for the t only, Okay, this is basically going to become, okay, let's put the constant value in front, e power 1 over minus 2a, e power minus 2a, and then upper value first, that is infinity, and then lower value that comes second. Okay, we can do separately as well. So it will 2a times infinity uh, minus e power minus 2a times minus infinity. So this one becomes 0. Okay, so 1 over minus 2a remains the same, and then here you multiply this one by infinity, then this e power minus infinity, that is 0, and then minus, and here we have e power minus minus infinity, so that's going to become infinity, right? Negative infinity, this is going to be infinity, so e power infinity is infinity, so we're going to have negative infinity, and negative negative make this one positive, so we are going to have infinity divided by some real number, so that's going to be infinity, so the answer is infinity, right? So this doesn't satisfy the energy signal, is because energy should be finite value in order to be energy signal, so this doesn't satisfy the energy signal condition. Now the same thing applies to power signal, and the power signal equation is given by Pg is equal to limit t approaches infinity 1 over t integration negative t by 2 to t by 2 g of absolute value square dt. And again, if we plug that function for this equation, this one becomes limit t approaches infinity, and then 1 over t integration negative t by 2 by 2, and then e power minus 2at e power minus 2at dt, and if we integrate this one, we will get e power, the top part remains the same, but we will have it divided by coefficient in front of t, that is minus 2a, so we can write this one as limit t approaches infinity 1 over, instead of putting the minus 2a right here, I can bring it to the front as well, because since anything that is not related to t is going to be a constant, so we can bring the minus 2a in the denominator to the front, and t remains as it is. And we are going to have this e power minus 2a, and this one goes from negative t by 2 to t by 2. Okay, now let's apply that one for this. So this is limit t approaches infinity 1 over minus 2at, and then this is going to be e power minus a 2 cancels because of t by 2, so we are going to have e power minus a capital T, we are replacing the t with t by 2 capital T, and then minus e power um, minus e power again 2 cancel, and this become plus, and then we are going to have power 8. Okay, a capital T. Now let's look at the situation. So first, if we apply infinity for this one, there's a situation, we are going to have negative infinity in the denominator, and here this one is 0, that's okay. 0 divided by infinity, that is undefined. So actually 0 divided by negative infinity is um so we are going to have a lot of confusion, right? So to avoid that, what we can do is we can take them separately. And here also, if you look at this is negative infinity over negative infinity, so again we are going to have a lot of confusion. So what I'm going to do is I'm going to do them separately, take the limit separately. Limit t approaches infinity, e power minus 8t divided by minus 2at and then here minus minus become plus here, and this one become e power 8t divided by 2at. Okay, and this one also limit t approaches infinity. Now let's try to apply infinity for this one alone. Okay, here if I apply infinity, this e power negative infinity is 0, and here this one is negative 2a t, that is infinity. So 0 over negative infinity, that's like a little bit confusing. So what we can do is we can apply L'Hopital rule whenever we have undetermined situation, undetermined, indeterminate, or undetermined situation. What we can do is we can just use the L'Hopital rule. L'Hopital rule is basically we do the first derivation and then apply the limit t approaches infinity. So if I use the L'Hopital rule for this one, this is going to become limit t approaches infinity, and the first derivative, this one is basically the power, the value in front multiplies. So this is negative a e power minus at, and in the denominator we are just taking the derivative with respect to t. In the denominator we're going to have just minus 2a. So here if we apply infinity, this is e power negative infinity, that is 0, so we don't have problem here. And let's try this one here. This one, if you apply infinity, this one infinity over infinity, again we have to use L'Hopital rule. So this one again become a power 8 times e power a t divided by 2a, and then limit approaches infinity, t approaches infinity, and this is infinity over 2a, so that's going to be infinity. So for this one it's going to be 0, and then for this one it's going to be infinity. So 0 plus infinity, that's infinity. So the answer is infinity. Therefore this one is also, this one is not a power signal as well. So this is neither an energy signal or power signal. That's what we want to prove. That's what the first part of this one is asking. And the second part is asking, the second part is saying that, however, if A is purely imaginary, it is a power signal with power Pg is equal to 1 regardless of the actual imaginary value of A. Okay, so we have to prove this one as well. If it's imaginary, what will happen to the power? Let's see that. Okay, case 2, A is imaginary value, and if it's imaginary, there's a real part and an imaginary part. So we can say, so let A is equal to J and X. Okay, so one is real, one is imaginary. J is the imaginary, X is the real one. Some people put JB, so it doesn't matter what you put, it's gonna be almost okay. And the equation for the power is given by Pg is equal to limit t approaches infinity, and then 1 over t integration negative t by 2 to t by 2 g of t absolute value square dt. But when we are dealing with the imaginary functions, um, this like okay. So if we are dealing with imaginary function, we had know one thing, that we multiply g of t with its conjugate, g of t conjugate, that is equivalent to g of t absolute value square. Okay, that one is what we are going to use here. So if we use that, limit t approaches infinity 1 over t, and then negative 1 over negative t by 2 t by 2 g of uh, g and g conjugate d of t dt. So this is going to become limit t approaches infinity 1 over t, and then negative t by 2 t by 2, and instead of this g, the given function is but e power minus 80. Instead of a, we are replacing that one with jx. So e power minus jxt, and then times e power, the conjugate is basically the opposite sign. If it's minus, that will become plus. So this be jxt and then dt. Now from this one, you can clearly see that when we have the powers, when we multiply with the powers will add. So this is going to become plus minus, and this is going to become 0, e power 0. Limit t approaches infinity, and then we are going to have integration of negative t by 2 t by 2, and e power 0 is 1, and then dt dt, and then this is 1 over t. Okay, and if we integrate 1, that's basically okay, if we integrate 1, that's integrate 1, what's gonna be, that is upper limit minus lower limit t by 2 minus t by 2. So minus minus become plus. So this is like, let's continue. Limit t approaches infinity 1 over t, and then t by 2 minus minus t by 2, that's plus t by 2. So t by 2 plus t by 2, that's t. Okay, then t cancels. Now there's no t to apply this limit, so the final answer is 1. That's what we want to prove. Pg is equal to 1 regardless of what value you have for the a. Okay, and that's all we want to prove. I hope you guys find this video uh, uh, I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.